Okay, guys, so today I'm going to look at Leaving Cert Physics 2020 paper question 1. This was the experiment to verify the principle of the conservation momentum, in which a body A was set in motion with a constant velocity. It was then allowed to collide with a second body B, which was initially at rest, and the bodies moved off together at a constant velocity. They gave us four sets of data: the mass of body A, which is 125.6 grams, the mass of body B, which is 111.1 grams, the distance traveled by body A for 0.2 seconds before the collision, which is 11.4 centimeters, and the distance traveled by bodies A and B together for 0.2 seconds after the collision, which was 6.1 centimeters. First thing we're asked to do is we are asked to draw a label diagram of how the apparatus was arranged in the experiment. Okay, so when you're drawing diagrams, the rule is there's no such thing as a diagram that's too big, unless it goes off your page. There is such thing as a diagram that's too small, and that is if it's just really hard to see. So in general, a diagram should be at minimum 1/3 the size of an A4 page. So first thing I'm going to do is I'm drawing my track. Now I'm going to draw my two little carts on the track. Always use a ruler when you're drawing your diagrams, which means in order to draw these diagrams fast with a ruler, you should practice them quite a lot. And if you've got your diagrams practiced by drawing them quickly and with a ruler, it just means that when you look at an exam paper question and you see draw a diagram, you will just get your ruler automatically and you will do the diagram extremely quick. So it's a nice way to buy back a little bit of time in the exam. So this there is my cart 1 and 2. I'm just going to draw a little bit of Velcro on the end because they do stick together. They are carts, so I'm just going to draw little tiny wheels on the side. And there we go, there. Right, next thing I need to do is I need to draw my means of recording the time. That is done by a ticker tape timer. So I'm just going to draw the ticker tape. Coming off, I'm going to draw the timer now in a minute. I'm just going to maybe delete that part there. Straighten that up, make it look a little bit better. Now, again, you practice these with a ruler and you'll get the quality of your diagram looking a lot better. So this there is a part of my timer. And then I just draw the timer sitting at the end. Now, it is a label diagram, so your diagram does have to be labeled appropriately. So, parts that have to be labeled for your marks are the ticker tape timer, ticker tape timer, and again, good, nice, big, clear diagrams, nice, big, clear labels, the ticker tape itself, your body A is right here. Because they have to stick together, your Velcro, and your body B. And of course, it is sitting on a track, so you have to label the track itself. So there we have the track being labeled. In order to get your full 9 marks, it's a big clear diagram that is labeled, and you have to show a means of coalescing the two bodies, which means making them stick together, which means we get 3 marks for our Velcro. You do have to show 3 marks to show how you're recording the distance and the time travel, which is the ticker tape and the ticker tape timer. And you do have to get 3 marks just for having the two bodies themselves set up on the track. So that diagram will be worth the full 9 marks. The next question that they asked us was describe how the time interval was measured. Now, the time interval measured has to be consistent with the manner in which you've drawn your diagram. I have drawn my diagram using a ticker tape timer, which means I have to give an answer of measuring it consistent with a ticker tape timer. Some people will have done this experiment using a motion detector and a data logger, and they'll have to give a slightly different answer. So what I would say is on the ticker tape timer, the number of gaps between 2 points is multiplied by 0.02 seconds to calculate time interval. Okay, so the main points there that will get you the numbers are the number of gaps between 2 points multiplied by 0.2 seconds. Because every gap on a ticker tape timer is 0.02 seconds away from each other. And that's how we do that one there. The next question, again, was also asking us about how the experiment was done and set up. So the next question asked us, how were the effects of A, friction, and B, gravity minimized? Okay, so the way we do that is to get rid of friction, or to minimize friction, the track is held at a slight slope. And the idea behind that being that if it's at a slight slope, gravity will try to pull the carts down slightly, but friction will try to push them back slightly. And if you get just a slight slope, then that effect of gravity pulling them down should balance off with the friction trying to push them backwards, and that should balance it off. How do you minimize the effects of gravity? Well, to minimize the effects of gravity, again, you try to aim that your frictional force is balanced with your gravitational force on the slope. Because if that happens, what you'll notice is that the acceleration is equal to 0 meters per second squared. Again, same idea. So when you have them at that slight slope, if there's too much of a slope, the gravitational force will overcome the friction. If there's not enough of it, the friction will be the one that wins. But if you find the right slope, then the gravitational force and the frictional force will balance each other out. Okay. Next question then that they looked for, and that was use the data to calculate the initial and the final velocities of the body A. Okay, so this question was actually quite nice because they actually gave you the data quite simply up in the original question. So if we go back to the original question, we can see that before the collision, body A traveled 11.4 centimeters in 0.2 seconds. And for body B, for body A and B together, which was just when they collided and then they started to move off together, we can see that it traveled 6.1 centimeters in 0.2 of a second. So we can now work out my initial velocity and my final velocity by using simple formulas where velocity is just displacement traveled over time. And again, velocity is displacement traveled divided by time. So the simple ways to do it, U comes from here, V uses this one here. So what we can just do is for the first one, U is equal to displacement 0.114 divided by 0.2. And if I just plug that into my calculator, I'll get you an answer for that now. So that means the initial velocity is 0.57 meters per second. So take note of what we had to do. We just took the initial and final velocity. So we took the distance from the data that they've given us. They gave it to us in centimeters. We converted it into meters. And we used the time, which is the time interval of 0.2 seconds, and we divide that in as well. To work out our final velocity, same idea. V is equal to 0.061 divided by 0.2. And again, we just worked that one out on our calculator. And that will give us a final velocity of, just let me work that out, 0.061 divided by 0.2, 0.305 meters per second. Okay. So in doing that there, we can now see what was the initial velocity just before the collision and the final velocity, which was just after the collision. The last question they want us to do is demonstrate how the data verifies the principle of conservation of momentum. So we are going to use those two numbers, and we're going to use other numbers back from the question. So part B, we know that momentum is equal to m times v. For the way this has been set up, we have our first cart A times UA plus the second cart MBUB is equal to MAVA plus MBVB. What this means is that the initial momentum of the car, of cart A, plus the initial momentum of the cart B is equal to the final momentum of the cart A plus the final momentum of the cart B. Now, something that we know here is that initially the cart wasn't moving. So since cart B wasn't moving, this essentially falls out of our formula. We also know that these two things stick together, which means I can put these ones together as well, which now means mass A times the initial momentum, or initial velocity of A, is equal to the mass of A plus the mass of B times their final velocity, which I was going to call VF. So now I have all the information that I need, and I can go back to my original question just to get the original masses. I know the mass of body A was in kilograms 0.1256, because it's 125.6 grams. And I'm going to multiply that by the initial velocity from my top of my question there, 0.57. That's equal to the mass of A and B together, which is 0.1256 plus 0.1111 times my final velocity, which is 0.305. So again, I just do these calculations on my calculator quick. (0.1256) multiplied by 0.57, and this initial velocity here is 0.0715 kilogram meters per second is equal to, and I do it on the other side, 0.1256 plus 0.1111 is equal to that, multiplied by 0.0305, and that gives me 0.0722 kilogram meters per second. So as I can see there from my numbers, that my initial momentum and my final momentum are essentially the same number. So I just write a quick little sentence that says, as the initial momentum is equal to the final momentum, all right, just move the screen up for you there. As the initial momentum is equal to the final momentum, the principle of conservation of momentum, PRINCIPRL, conservation of momentum is verified. Okay, and once we have all that in, guys, that will give us our full marks.